open. Sorry about that. That's probably going to slow down the system, but let me see if I can get one of them to close. I'll cancel that. Okay. Well, I don't think I can. It's not going to let me. All right, we are recording, though. I can't get this off the screen. Okay. One of these needs to stop. Which one? Let's see if I can cancel that. Ah! Worked. Okay. Now let's get this set up for slideshow. Boy, this thing is so slow. Okay. From current slide. Okay. All right. Everything's taking forever this morning. So, as soon as it comes up, well, still not. Okay, we're up. What were the questions?
About a problem having
The difference question?
Right, it's number 7.
Okay.
I know that you plug in the function.
Right.
I'm confused on what to plug in where.
Okay.
To simplify it.
Okay, can you find one like it in the book?
I looked at example.
Okay.
Which is on page 43.
43.
Right.
Okay.
I know you have to plug in. That's all I know.
Okay.
And when it came to plugging in, I screwed like everything.
Okay. Let me.
Subtract both of them because it's the difference.
All right. Why don't you look at page 48, the homework exercises, and there's several there. Are any of these closer? Would they be more helpful to you than the one that you are looking at?
What number?
Page 48, 73 to 80. Would that be helpful to do that rather than the one that you were looking at?
I would plug in x squared minus 2x plus 4
Okay.
in place of.
Okay, where are you looking? Okay, you're doing 73?
Right.
Okay.
I would just plug that in right there.
Okay. Well, you want to do that one?
Yeah.
Okay. All right. Let's see if I can find a clean figure here. All right. I think that's as clean as we're going to get. Okay, let me get my pen set up. All right. So we're doing page 48. This is 1.4 exercise. And number 73 is the one you chose? Okay, 73. Okay. Here's the problem. In these exercises, find the difference quotient and simplify your answer. Pretty similar to what it asked for, right? Okay. So here's the function. F of x is equal to x squared minus 2x plus 4. Right? And what they're asking for is f of 2 plus h minus f of 2 divided by h, as long as h is not equal to 0, because you can't divide by 0. So, where are you suggesting we start? Plug in what? A little louder? I can't hear.
I'm going to say x squared minus.
Okay, wait. What are you looking for? you've got f of x, right there it is. What are you looking for? Say again? Okay. What's the first thing you're looking for? The difference quotient, for sure. There's the difference quotient. What's the first thing you need to know to use that difference quotient? Say again? Okay. I think you're saying right, but tell me what to do. Plug in 2 plus h where x is, right? Okay? Because that's what it's asking for. So we need to know what f of 2 plus h is. That's the first thing. Now, how do we get that? Say again? A little louder. Wherever you see an x, plug in 2 plus h. So you tell me what to plug. 2 plus h squared minus 2 times 2 plus h. What's more? Plus 4. Got it. Let's figure out what that is. Okay? What's 2 plus h squared? Say again? Okay. 4 plus 4h. Okay, I used to be in that. Okay. Now, why is that? Look what he's doing. Square the first, twice the product. 2h is the product, twice that would be 4h, and then square the last. Now, that's the shortcut. Okay. If you don't remember the shortcut, go off to the side here and do 2 plus h times 2 plus h and FOIL it. Okay? That's what 2 plus h squared means. And you'll get the same answer. 2 times 2 is 4. Then you get plus 2h, that's plus 4h. That's twice the product, plus h squared. Got it. Next. Minus what? I can't hear. Minus what? Minus 4. Minus 2h plus 4. Okay, let's do a little bit of simplification as we can. What can we do here? Okay, say a little louder, I can't hear. H squared? Okay, I'll write down h squared. Say again? Plus 2h, I heard that. Okay. Plus 4. See how she got that? Okay. Say this 4 and this 4 add to 0, so those are out of there. These two add to plus 2h. That doesn't have anything to add to, so that's just h squared. Since these two disappeared, all you have is plus 4 left. Okay, so there's your f of 2 plus h. What's the next thing you need to know before you can plug in? F of 2. So let's do f of 2. And what would f of 2 be? 2 squared minus 2 times 2 plus 4. Okay, and what does that come out to be? 4 minus 4 plus 4. All right, we're stuck on 4s, aren't we? Okay, can we get your name, please? Ebony, got it, thank you. Finding, there you are. Okay. All right, good deal. All right, what does that end up being? 4. Okay, I'll just leave it like that. So let's plug in what f of 2 plus h is. What is that? No, 2 plus h. That's your h squared plus 2h plus 4. That's what we found. That was the f of 2 plus h. Minus, what was your f of 2? 4. Okay, got that done. Divide by h. Okay, what can we do to simplify? Oh, 4 minus 4 is 0. Okay, so that leaves us h. Okay, factor out an h. Is that what I heard you saying? I thought so. Okay, all right. And what does that give us? H plus 2 divided by h. Now what can we do? Yeah, the h's divide out to be 1, and that's what your difference quotient is right there. With h not equal to 0, but if h gets close to 0, that's getting close to 2. Good deal. Does that make sense? Does it help?
Yes.
All right, good deal. Okay. So I think just about all these you can find homework exercises, several of them that will be very similar. Any other questions? Okay. Ready to go back to where we were, which was we were somewhere over here. All right, we were somewhere on this slide. Okay, we were talking about the squaring function. What can you tell me about the increasing, decreasing constant nature of a squaring function? F of x equal x squared. Okay, I see them drawing in the air. That's pretty. Okay, what does that tell you about increasing, decreasing? Say again? The squaring function, yeah. Alpha x equal x squared. Yeah, decreasing from negative infinity all the way down to 0, and at 0 it starts increasing from 0 to positive infinity. So there we have it. Graph is decreasing on the interval negative infinity. Always precede that by parentheses. In fact, when you're talking about intervals for increasing, decreasing, generally a good idea, just put them all in parentheses. Don't worry about brackets then. Up to 0, and then from 0 it's increasing. Okay? So that's why we usually leave out 0, because it's neither increasing nor decreasing there. It's pausing there and then going on. All right. Is there any symmetry in that graph? Okay, symmetric about the y-axis, which is the same as saying what? It's an even function. Very good. Does it have any, what is its, or its intercept? Does it have any? 0, 0. 0, 0 is the x-intercept. 0, 0 is the y-intercept. That's the only one. And that happens to be a relative minimum because it's less than all the other points around it. Okay? There's the graph of the squared function. Does that make sense? All right. Then let's move on to, say again? Okay, I can't hear it. A little up. We did do that?
Yeah, we did some transformations.
Oh, that's right. I forgot I was in the other book. Okay. Okay, we already finished 1.6. We're on transformation. I thought that sounded awfully familiar. So let's get out of this. Yeah, that's what I was thinking. We had gotten pretty far, but see, I put the mark in the other book, not in this one. So, how far did we get? Let me see. I do have it in here. Let me see. Thank you for reminding me. I was going to say, this looks like stuff we've already done. I have that we're on example 5C. Is that right? No, that's in my other text. Okay, got it. Wait a minute. I'll get in the right course in a minute. We're example 3 at the top of page 70. Is that right? Yes? Finally. Okay. Page 70, example 3. All right, let's get out of this one. All that to get in there, and now, okay, let's go with yuck. I have to go through this again. Word. Well, it's a little faster than it was the first time. Not a whole lot. Okay. Resources by chapter, chapter 1, PowerPoint lectures, 1.7. Okay. Now we wait for PowerPoint to go through its long, or hey, much faster this time. I say, it's only opening. Now it's processed. Oh, here it comes. Good deal. Now we'll get down to here. Okay. we're going to reflect on some graphs here. Okay. Let's get slideshow set up from the current slide. Okay. Got it. Okay. That's right. They had left off example 3, hadn't they? Okay. And this is talking about it some, but let's go back to a slide that we can actually do example 3. Okay. Ooh, let me get my pen reactivated. Again. Okay, here we go. All right. Compare the graph of each function that's coming with this function, f of x is equal to the square root of x. Okay. Now I'm going to draw the graph of it. Or you're going to help me draw the graph of it. What are some points on that graph? 0, 0. Good start. Okay? Wait, let me do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, what? 1, 1. There we have it. Say again? 4, 2. Okay, right about there. Okay. Okay. I don't think I can reach 16. 1, 2, 3, 4. 9. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 3. And if I could, I would do a 16, 4, but let's see. 1, 2, 3, 6, 7, 8, 9, 10. Yeah, can't do it. So here's what it looks like. We've seen it before. What do we call that? Half of a sleeping parabola. Right. Okay. There is our base function, our parent function. Okay? Now, the problem, you give me a color. Blue. Light blue. All right. Baby blue. Carolina blue. Okay? The A part here is g of x. Can you see that well enough? Is equal to, you can't? Oh, you can? Okay. Minus the square root of x. What are we going to do to get that? Okay. Yes, you're negating the y, so reflects over the x-axis, okay? So that would be, this one goes, it stays 0, this goes to -1, that goes to -2, this goes to -3, and it's this one. That completes your parabola, it doesn't. That's g of x is minus the square root of x, okay? So that is your, you negate the y, so you flip across the x-axis. Make sense? All right, another color. Red. Okay. If I can get red to come up. There we go. Now we're going to do h of x. And h of x is going to be the square root of negative x. Wait a minute, can you do that?
No.
Okay. Say you can't take the square. Oh, if x is negative, then you can negate the negative number, and it becomes positive, then you can take a square root of it, can't you? Okay, so you can do that. But you're right in thinking this thing in here can't be negative, so therefore x can't be positive. So therefore, what have you done? Yes, you reflect across the y-axis because you negated the x. That's your reflection there. So here we have a 0, 0 is still there, but now when you do a -1, it gives you 1. When you do a -4, it gives you 2. When you do a -9, 1, 2, 3, 4, 7, 8, 9, you get a 3. Okay? So there's your half of a sleeping parabola, something like that. All right, one more. How about K of X? What color you want K to be?
Yellow.
Yellow. Can you see that, you think? Okay. Here's K of X. How is that? Is that all right? Okay. K of X is equal to minus the square root of X plus 2. Minus the square root of X plus 2. Okay? All right. He's saying because you're messing with the X, that's going to be a horizontal shift. And he said left, because with X's you always do everything backwards. Okay? So that's going to be left 2. And then you're going to negate that. It might be better to do the reflection first and then shift 2. That makes it easier to see. So you do the negation here, which gets you down there, just like with baby blue, and then move to the left 2. So take baby blue and do left 2, okay? That would be 0, 0. That one there. And this one here. And that's 1, 2, 3, 4, 5, 6, 7, 8, 9. This one would be here. So here's your half a parabola. Okay, I didn't quite draw them very well, but that's what it looks like. Does that make sense? Okay. Now, if you look in the book, you'll see they're all in one graph, but you might see them a little bit better. All right. Any questions on those? That then is you also have a checkpoint. Now, what follows this is talking about this stuff right here. So keep this picture in mind, and let's go back to this. When sketching the graphs of functions involving square roots, remember that you must restrict the domain to exclude negative numbers inside the radicals. Okay? For instance, this one, what's your domain? X greater than or equal to 0, because what's in here has to be non-negative. How about this one? Less than or equal to 0, because what's in here has to be non-negative, in other words, positive, and this has to be greater than 0, so therefore minus X has to be less than 0. Okay, how about this one? Say again? Than 2? Negative 2, okay. Because, and let me show you how I do that. I don't know, the book doesn't actually show this that much. Let's take this second one. Let me get back to black here if I can, or dark blue. Okay. This right here, let's do this one. Okay. To do that, we say, what's in the radical? Minus X has to be greater than or equal to 0. What's inside the radical has to be greater than or equal to 0, right? Now, what do you do next? You're looking for X. Say again? Multiply or divide by negative 1. So that makes it X is? Anytime you multiply or divide by a negative number, you flip the direction of the inequality. Now, if that was a not equal to, yeah, not equal to doesn't change. It's still not equal to. If you were adding something or subtracting from the same side, never changes. If you're multiplying or dividing a positive number by what's here, doesn't change. It's only when you're multiplying or dividing a negative number, you flip the direction of the inequality. Okay? Here's another way we could have done that. We could have added an X to both sides. That would make this 0 is greater than or equal to X, which means X is less than or equal to 0. So you could have done it either way. That's how you do that. So let's now do the next one. Okay? What can you say about the inequality if you're given that problem? Not the inequality. Well, what do you say about the domain of that? How do you set it up? Yes, you take what's inside the radical x plus 2, and what can you tell me about it? It's got to be greater than or equal to 0. Anything you take the square root of has to be greater than or equal to 0. Okay? Now, what do we do with that? Subtract 2 from both sides, and that gives us x is less than or greater than or equal to negative 2. Adding or subtracting negative numbers, no problem. You keep the sign the same. It's only when you multiply or divide that you flip the sign. So that gives us x greater than or equal to negative 2. And if we look back here, that's exactly what it is. X is greater than or equal to negative 2. That was the graph. So sure enough, that is it. Does that make sense? Kinda. Okay. All right. You just take what's inside the radical, whatever is inside there has to be greater than or equal to 0, and then solve for the x. Okay? Remembering, the only time you change the direction of that is if you multiply or divide by a negative number. Adding and subtracting, no. Multiplying and dividing by positive numbers, no. Only multiplying or dividing by negative. Okay. Now, I think we're ready for non-rigid transformations. Okay? Horizontal shifts, vertical shifts, reflections are all rigid. The shape of the graph does not change. If you can use your imagination, this graph looks like this. This one looks just like it. It's just reflected. This one looks just about, sort of looks like it. If I'd have stayed on the dots, it would have looked like it. And this one even looks like it. You just flip and move, but they're all the same shape. Just different orientations. Okay? Now, those transformations change only the position of the graph in the coordinate plane. Its orientation and position. However, we have non-rigid transformations. Those that distort the graph. Now, how do we distort it? We stretch it, shrink it, in either horizontally or vertically. Okay? So let's take a look at that. For instance, a non-rigid transformation of the graph, and by the way, what made those translations? Shifts. Horizontal. What? Something is being added or subtracted. That gave you a horizontal shift. If it's added or subtracted from the x. If it's added or subtracted from the y, that's a vertical shift. Negated, that's flipped. Either horizontally or vertically. But we left off multiplying and dividing, didn't we? What happens if you multiply, not add or subtract? If you started with y is equal to f of x, and then your g of x is c times f of x. Okay? Where the transformation, that's number one is vertical, because what are you changing? The y, and y is vertical. So it's a vertical something. It's a stretch if that c is greater than 1. If it's equal to 1, you didn't change a thing. If it's greater than 1, you increase the y values. You stretch, multiply by a big number. However, if the c is between 0 and 1, you shrunk it. Right? Because now your g of x is smaller. Because you multiplied whatever your f of x was by a number between 0 and 1. That's a vertical shrink. That's a psychologist who stands up. No, I'm just kidding. Okay. So, were you going to ask something? Okay. Another non-rigid transformation of the graph y is equal to f of x is when you multiply, and by the way, or divide the x. This one you multiply and dividing the y near the x. So guess what kind of transformation this is? If you horizontal. And it's either going to be a stretch or a shrink. Okay? This time the psychologist is lying down. Okay. Now, what do you remember about the things with x? Always backwards. Remember, it's backwards. So therefore, if you multiply the x by a constant, then the transformation, if that constant's a big constant, you're shrinking it. If it's a small constant, between 0 and 1, you're stretching it. Okay? Strange but true. Everything is kind of backwards when you're doing it to the end. Right? Okay. And you'll see why if you plug in some numbers. Okay? So let's do one. Compare the graph of each function with the graph of f of x equal absolute value of x. So I'm going to draw the graph of the parent function, f of x equal absolute value of x. Actually, you're going to draw it. Let me. Okay, we won't need that, but I'll put one down. Give me some points. 0, 0, good. Second? Okay, you're doing this one. Yeah, no, yeah, okay. 1, 1. 2, 2. 3, 3. 4, 4. 5, 5. 6, 6. 7, 7. 8, 8. Blah, blah, blah. Okay. Horizontal, straight line, slope of 1, going up there. The identity function on the right. How about on the left? Second? Okay. Yeah. So negative 1 will be a 1. Negative 2 is a 2. Negative 3 is a 3. Negative 4 is a 4. Negative 5 is a 5. So you're doing the absolute value. There's your absolute value function. We recognize that. That's the identity function here, and then the negative identity function there. Okay. Now, what color you want H? Second? Orange. Okay. All right. H is going to be 3 times absolute value x. What are you doing? For every f, y value for f, you're multiplying by 3. So 0 times 3 is? Okay. This was, the y was 1. 1 times 3 is? 3. Same x. Okay. And this one was? 2. That would be 6. Okay. 3, 4, 5, 6. Somewhere up here. Okay. There it is. So here's what your left-hand side becomes. How about the right? The right-hand side becomes the left. Yeah, that's a 3. And that's a 6. Oh, well, come over here. Okay, so there's that one. So there's what it's done. Do you remember those little toys that had strings on, sort of like puffets? You pulled the string and the arms go up. That's what you did. You pulled the strings and all the values went up 3 times. Okay? Does that make sense? That's a vertical stretch. Vertical stretch. You multiply by a number greater than 1, but you multiply the y value by something greater than 1. Okay, let's do G. What color you want G? Second? Purple. Okay. All right. What are you doing to G? A shrink, a vertical shrink. Okay? So this would be 1/3 of 1, 1/3 of 2, which is 2/3, 1/3 of 3, which is 1, 1/3 of 4, which is, you got the idea. It's that, probably too much there. 1/3, 2/3, 1. Okay, so it keeps going like that. Something like that. I can't draw very well. That time the elephant sat on it, didn't it? Okay, you shrunk it vertically. Okay, make sense? Yay or nay? Okay. All right. Yay. All right. Good. Okay. Let's clear that, and let's see how they do it. Well, there's the graph, the light gray they did of your absolute value function. Then we're multiplying by 3, vertical stretch. You pulled all those up. Now, actually, you didn't pull them up. That would have been a shift. You stretched them up. You multiplied. 0 times 0 is 3 times 0 is still 0. 3 times 1 is 3. 3 times 1 is 1 here, is 3 there, and all those pulled up by 3. 3 times what they were before. And the second time, you multiplied by 1/3, which was decreasing. So it was a vertical shrink. And so this 1 became 1/3, 2 became 2/3, 3 became 1, and so on. This 1 became 1/3, this became 2/3. Make sense? All right, theirs is almost as pretty as mine, but not quite. Okay. Whoa, last slide. Can you believe it? Let's do example 5. Okay, I think let's do example 5. And by the way, example 5, this is new in the new text. It says, see larsonprecalculus.com for an interactive version of this type of example. They don't say that on all the ones they don't show on the slide set, but they do it on some of them. So let's do this one. Compare the graph. Oh, I'm still purple, am I not? Let's do back to dark. Okay. Compare the graph of each function with the graph. All right. Name, please. Sean. Okay, good deal. Okay, good deal. Okay. All right. I was lost there. Okay. Alpha of x, here's our, it's not really a parent function, but our original function, alpha of x is equal to 2 minus x cubed. Ooh, boy, how are we going to do that? Say again? Let me tick off a few points here. 1, 2, 3, 4, 5, 6, 7. Negative 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. Okay. Whoa. How are we going to do that? Say again? Yeah, we got to do, yes. I'm sorry? Okay. So, what we're going to do is start with the parent function here, which would be x cubed. And we got a long way to go before we even start changing it, okay? So x cubed would be 0, 0, 1, 1, 2, 8, right? 1, 2, 3, 4, 5, 6. Somewhere up there. This will be a minus 1, then it's a minus 8. So it's going to be something, I'm just going to dot this in because we really don't need this. Okay. There's your x cubed function. Okay? And what's the first thing you do to x cubed? Negate it. So what's that going to do? It's going to flip it. So that goes there, this goes here. So now it's like this. Right? Okay, so what I'm going to do is get rid of the other one because it's sort of confusing and get rid of this one. I did have to dot it so it's harder to erase. Whoa. Okay. What's that? Okay, across the x-axis because you're negating the y value. Okay? Okay, remember, if this was a plus 1 here, 1 cubed was 1, but when you negate that, it becomes negative 1. That's what's across the x-axis. Okay? Now, what are you doing? What's the next step that you're doing? Say again? I can't hear. I hear something going on, but I can't make it out. Is that a left? Up 2. Okay, just don't say yours. Okay. So up 2, this one goes, whoa, I better get that off. Okay. So this goes, yuck! Okay. This one goes up 2. That's more than 2. Let me put the 2 there. This goes up 2. That goes to there. I can't go anymore. This one goes up 2. That goes to there. So here's, ooh, I went too far, didn't I? That one. So here's what it looks like. Now your curve is like this. So this is, whoa, this is that. This is finally our parent function. So let me get the other stuff out of the way here. Okay. Not parent function. That's our original function. That is f of x equal 2 minus x cubed. Okay? You had to do x cubed, reflection, and a vertical translation. So that's what we got for that. Now we get to the problem. It says, what color you want G to be? Green, light or dark? Dark, okay? G for green, that makes sense. So our G of x is going to be f of 2x. Oh my goodness, what are we doing here? Horizontal shrink. Okay. Because remember, whatever you do horizontal, it makes it in reverse. So you're shrinking the x by 2. In other words, taking half. So half of 0 is still 0. You keep the y's the same. Half of this was a 1 here, so half of that becomes a 1/2. This was a -1 here, somewhere up there, and half of it becomes that. So basically, it's this very similar function. It's a horizontal sandwich. Shrink. You press them together. Horizontal shrink. That's what your f of 2x is. See, they don't even say what to do with the other. Now, what color you want? H? What color you want H to be? Blue, light or dark? The medium? Okay, that one. Okay, good. Now we have h of x is equal to f of 1/2 x. Multiply your x values by 2. Okay? So this one was 0, 0. Multiply that. 0 by 2. 1, 2 is that. The next one was a 1 here. So you make it a 2 here, but you keep the same y value, not, okay. Mess that one up. Okay. Okay. Here we went -1 on this one, so this will go -2. And it's right there. Okay, so that's where it is. So this one now looks like this. That's a horizontal stretch. See that? Horizontal stretch. Okay? And if you look at the figures in the book, the first one, the green one's a horizontal shrink because the number greater than 1 multiplied by the x, so it's going to be horizontal, but you always go the opposite direction there. It shrinks it, and when you multiply by something between 0 and 1, then that's a stretch by a factor of 2 as well. Make sense? There is a checkpoint, and all the checkpoints have audio-video solutions at larsonprecalculus.com. All right, let's do the vocabulary, top of page 72. Horizontal shifts, vertical shifts, and reflections are blank transformations. Rigid, very good. A reflection in the x-axis of a graph y is equal to f of x is represented by h of x equal negative f of x. Yes, very good. My hearing's not good. While a reflection in the y-axis of the graph of y is equal to f of x is represented by h of x equal f of negative x. Perfect. Number 3. A non-rigid transformation of the graph y is equal to f of x represented by g of x equals c times f of x is a blank blank when c is greater than 1. Vertical stretch, okay. And a blank blank when c is between 0 and 1. Vertical shrink, you got it. Okay. Number 4, matching. Okay, match each function with the transformation it represents. Always assume your c's here are positive. So h of x is equal to f of x plus c. What is that? Vertical shift. Okay. Up or down? Up. So that will be Roman numeral 4. C units up. Number B. H of x is equal to f of x minus c. C units down, that's number Roman numeral 2. C, that's yes in Spanish. H of x is equal to f of x plus c. Horizontal shift to the left, that will be 3, Roman numeral 3. And h of x equal f of x minus c to the right, and that's Roman numeral 1. Okay, homework exercises. I gave some of these before. Here we go again. Any of the, either 5 or 7 or both. Do number 9. Okay? Do 11 or 13. Okay? Or both. Do any of the odds 15 to 19. 15 is at calcview.com. All of the odds are at calccheck.com. Calccheck.com. Okay? Then do any of the odds 21 to 37. And 21 is at CalcView. All of the odds are at CalcChat. Do any of the odds 39 to 45. 39 is at CalcView. All the odds are at CalcChat. Okay, then do either 47 or 49 or both. And then do any of the odds 51 through 55. Then do 57 or 59 or both, and try to do 61. Not a bad idea to look at 63 and 65. They're true false. You won't see many of those on the test, but still look through it, think through it. And then you can probably think of, play around with some of those others if you choose, 67 through 71. Now, let me point something out to you. Several of those homework exercises, you first started, they gave you functions, you sketched the graph. Then, they either gave you the graph and said, you name the transformation. Guess what, team? You're going to see both of those. One will be describing what happens and doing the graph. The other will be showing the graph or talking about the graph, and then you come up with the transformation. Yes? Not at all.
Okay, remember, when you find the zeros of the function, you said the denominator can never equal 0. So for the answer to that, like say if it's 5x at the denominator, you just put x can't equal negative 5.
Okay. Can you refer, I missed part of the first of what you said. Let me, somewhere here, oh, here it is, I got it. Which one are you talking about?
I'm talking about number 8.
Number 8.
The denominator, I know the denominator can never equal 0.
Right.
So, in the answer, you would say, like I'm saying, if it was 5x at the denominator, you would say x cannot equal negative 5.
Okay, because 5 times negative 5 is?
No, I'm saying, if you put x, never mind.
Okay, got it? All right.
Never mind.
Okay. Did that, I think it answered your question, didn't it?
Yeah.
Okay, good. All right.
I know.
Yeah, you, whatever that denominator is, it cannot equal 0. Okay, just like things under the square root cannot be negative. They have to be greater than or equal to 0. You know, the denominator can't be equal to 0, solve for x. Okay, solve for x. Okay. Now, and notice there were several like that. 9 and 10 gave you the functions. You draw the graphs. 11 to 12 gave you the graph. You write what the description was. 15 to 20 gave you the graphs. You write what the transformation was. 21 through 38, they give you the transformation. You write, you draw the graph. So be ready to go both ways. Now, even more so, 21 to 38 gave you the functions. You describe what happens. You don't have to draw drawing the graph, but tell about all the shifts, all the reflections, all the compressions, expansion, stretching and shrinking. Yeah, I couldn't think of the word. Okay, but then on the 39 to 46, they tell you what happened, then you give what the new function is. So you see, 21 through 38, they gave you the function, you describe the changes. 39 to 46, they describe the changes, you give the function that represents that. Be ready to go both ways, offense and defense. Yes? What's that again? Usually about twice what the quiz is. It may not be exactly 20, but it'll be close to it. It'll be 2 pages, and this isn't strict, but it's pretty close. The first page will be a lot like your quiz, not the same questions, but tested over the same stuff, and the second page will be the second half of what we've done, the next 3 sections that you haven't been quizzed on. Now, sometimes one question will find its way onto the previous or next page, but generally that's going to be the case. About twice what the quiz is. Okay? Now, I believe we're through with that, and we're ready to go to 1.8. Right. Your test, you will have a test on material you were quizzed over and on that you weren't quizzed over, right? Okay? But I don't have time to give you a quiz and get it back to you and give you a test. That you just don't have time for that. All right. So let's move on to 1.8. Yes. What's that? I gave away my last one. Okay. Why did she not give me enough quizzes? I'll have to go down and make a copy. Wait, maybe, let's see. I might have one. Hold on just a second. I didn't go through and see if I had any old ones. I thought I had looked before. Nope, I don't. Okay, so I have to make a copy at the end of the class. So can you come back and pick it up? I mean, come with me and I'll make the copy. Does anyone else need a quiz? Okay. So remind me to run down and make one when we're gone. Okay, 1.8, continuing chapter 1. Slideshow from current slide. Still doing functions in the graphs. Now we're going to be combinations of functions and composite functions. Now the first part of this is going to be pretty straightforward. You've added, subtracted, and multiplied and divided before. The only little difference is what you do about domains, because functions deal with domains. Then the second part, composite functions, I'm guessing that most of you probably haven't done those, so we'll be doing that. So we're going to start with the simple stuff, adding, subtracting, and multiplying and dividing functions. Okay? Then we'll move on to finding composition of one function with another function. That's the sort of a new concept. And then we'll use the combinations and compositions to solve some real-life problems, which is why we do this in the first place. So let's first look at the arithmetic combinations of functions. Adding, subtracting, multiplying, and dividing. Pretty straightforward here. Okay? Just like when you add 2 real numbers, you get a real number, right? Subtract 2 real numbers, you get a real number. Multiply, divide, whatever. Okay. 2 functions can also be added, subtracted, multiplied, divided to get new functions. Okay? That's what we're going to be doing. So here's an example. Here's a function, f of x equal to 2x plus 3. Here's another function, g of x is equal to x squared minus 1. They can be combined to form a sum, a difference, a product, and a quotient. So let's start with the sum. What would you think the sum would be of those 2? F plus g. X squared plus 2x minus 4. Does everybody see that?
Yes.
You're adding f to g. This has an x squared, that doesn't, so it's x squared. That has a 2x, this doesn't have an x term, so it's plus 2x. This has a minus 1, that has a minus 3. You add those, you get minus 4. What if you're taking the difference? Well, let's see, they're only doing the sum here. So x squared plus 2x minus 4. Perfect. That's the sum. But what happens about the difference? Now, let's go back for a moment. When they did this, doing the sum, they put the f function in parentheses, the g function in parentheses. Not a bad idea to help you see what's going on. But guess what? A parentheses at the beginning of an expression doesn't do a thing to it. Now, if you had a number or a sign out in front of it, yeah, you have to have it. With this, you can lose those parentheses. A plus sign in front of parentheses, you can lose those parentheses. Now, if it's plus 3, then you have to multiply the 3 to it. But just a plus sign or nothing in front, you could just lose the parentheses and combine like terms. However, when you have a subtraction, you better put parentheses here. Here it doesn't matter, but you better put it here. So what would that give?
Negative x squared plus 1.
Okay. Yeah, that would be negative x squared plus 1. Then you're adding that to here.
Negative x squared
Plus 2x.
Minus 2.
Minus 2. You got it. Negative x squared plus 2x minus 2. Okay, what you think multiplying the two functions together?
2x.
Good old FOIL, isn't it? Multiply. 2x cubed minus 3x squared minus 2x plus 3. You got it. 2x cubed minus 3x squared minus 2x plus 3. Very good. Just before. Okay? Now, how about dividing two functions? Just write it down. Okay? Now, if either of these are factorable and they have common factors, you can divide them out. You know, do that. But there's one thing here you've got to watch out for. X squared 1 minus 1 cannot equal 0. That was not a problem ever before, but now it is because you put it in the denominator. Well, what would make x squared minus 1 equal 0? X either plus 1 or negative 1. So now you have to exclude some values from the domain that were there before. There was no problem here on the previous page. There is a problem now because you put it in the denominator. So that's the only thing you have to remember about dividing functions. Okay. Now, really domains do enter the picture. They haven't talked about them yet, but these two functions were polynomial functions. Was any limit on the domain? No, that's all real numbers. What if one of these had a square root in it? That would limit the domain, potentially. Or if one of these had a denominator with a variable in the denominator. That could limit the domain. So if you have limited domains to begin with, before you can add, subtract, multiply, or divide, you have to make sure you have the same domain. So if this function was from negative infinity to plus 3, and this function was from negative 2 to positive infinity, then the sum, difference, product, everything would have to be just between minus 2 and plus 3. You have to limit the domain to whatever those functions are. But most of the time, you'll see that and it makes perfect sense. This didn't show, so this was just polynomials. So, you got it. So the domain of this is what I was just saying, the domain of an arithmetic combination of functions, f and g, consists of all real numbers that are common to both of the domains. That's what I was just saying. You always start all real numbers, unless there's some restriction. You restrict this, then you have to stick with those common to both. In the case of a quotient, you have one further restriction. Anything that made that denominator equal to 0, you have to restrict that as well. So you had some restriction maybe on g to begin with, but then you added some more. If g of x could have been 0 up there, it can't be it down here. So you have other restrictions possibly. Okay. So here is the description of it, sum, difference, and product, and quotient of function. F and G are both functions with overlapping domains. Now, if they don't have anything in common, you can't do them, okay? But if they have overlapping domains, then for all x's common to both domains, the sum, difference, and product and quotient functions are defined as follows. The sum function is the two functions added of the same variable is the same as the function of one plus the function of the other. Difference is the difference of the two functions. The product function is the product of the two functions, and the quotient function is the quotient as long as that denominator is not zero. Okay, I think we just ran out of time, didn't we? And we were just about to start with example 1, so that's where we'll start next time with example 1. All right, good deal. And I'll go get a copy for you. Let me turn this off.